Welcome to the course on advanced power electronics. We have a topic today: EV chargers, type, design, and various topology of these chargers. So, starting for outboard chargers, the outboard chargers they are not in the vehicle. So, this outboard charger characteristic is supposed to be a higher transfer of energy, address the battery heating issue, weight on electric vehicle is removed, more better BMS system, battery management system, no flexibility rule to charge at various places, power output limitations is concerned, with capability of battery to accept the charge. So it provides the fast charge. It should provide fast charging, more better contextual approach opportunity for utility company and charging site owners, charge at higher power level, more complexity and higher cost, and combining the BMS in charging station is also cost intensive and complex, and less complex BMS system for charging. These are the typical example of cases in electric vehicle outboard charging. So it may be on the highway as a fast charging in 15 to 20 minutes, or it can be as a commercial DC or AC charging in 30 minutes to 120 minutes, and in offices again AC or DC charging 30 to 50 minutes, 120 minutes for fast and 8 hours for work day, and in home AC again AC to DC charging 8 hours overnight and 2 hours in top up. Now these are standard for onboard EV chargers. There are various standard SAE J1772 EV coupler for conductive charging, and SAE J1773 EV inductive coupled charging, and similarly SAE J1797 recommended practice for EV battery module packaging, and SAE J2288 life cycle testing of battery modules for EV, and SAE J2464 EV hybrid electric vehicle rechargeable energy storage system safety and abuse testing, and SAE J2836 part 1 use cases for communication between the PEV and utility grid, and SAE J2836 part 2 use cases for communication between PEV and supply equipment. Well, so there are many more standard. For this or outboard charger, like SAE J2836 part 3 communication between plug-in vehicle and utility grid and reverse flow, and SAE J2894 power quality requirement for plug-in vehicle chargers requirement, IEC 69/156 CD 2008 electric vehicle conductive charging, and IEC 23H22/TD2010 plug socket outlet vehicle coupler and vehicle inlet conductive charging of EV, and JVS C601.2000 plug and recharge respectable for EV charging, AIS 138 electric vehicle conductive AC charging system ARA. So this is typically a structure of outboard charging system like a low frequency isolation. So with the low frequency isolation we have a AC grid, then we have a isolation transformer power frequency charging, then we have a filter followed by the central AC to DC state, then the control DC link, and then non-isolated GT-DC stage, and then output filter, then goes to the typically for charging of the battery. This is general structure of an outboard battery charger with low frequency isolation. Coming to high frequency isolation in your outboard charger with the AC grid, then we have input filter, then we have a directly AC to DC converter, normally the control AC DC converter, then the again high frequency, then again DC to AC converter for high frequency isolation for DC DC stage, then we have again rectification, and then we have a filtered DC for the charging. So this I have a high frequency, but of course these are because of large rating, normally we are all having a bidirectional features like. Then typically architecture with another architecture with the isolation step down transformer for common AC bus charging. So we have a AC bus, then we have a rectification, and then DC DC converter for the battery charging with the kind of multiple maybe on charging station like. So this is for again another kind of architecture, isolation and step down voltage is provided by transformer, and then we have AC to DC converter, and we have a the DC link, common DC link, and we have a typically does DC bus charging station with several batteries, that called DC to DC converter based charging. So coming to first to common AC bus architecture, in this structure, each charging unit has its own rectifier stage that is connected to a common AC coupling point in the secondary winding of the step-down transformer. And this architecture represents a simple concept and has been used for years, and well-developed standard and technology are available. And furthermore, it needs lower power rating front-end stages, which can be either passive or active. However, the presence of several battery chargers with independent rectifier stages and inherent low power factor operation may produce unwanted harmonic effects on the utility grid, particularly for high power fast charger. So moreover, the cost of several converter units with lower power ratings is higher than that of a single high power converter unit due to the need of several filter sets, control stage and sensors. Now coming to common DC bus architecture, the alternative approach uses a single AC-DC stage with higher power rating to provide a common DC bus. And common DC bus feeds several battery chargers and provides a more flexible structure which can easily integrate distributed renewable energy conversion system or energy storage devices. And these systems are essentially DC, and DC connection is characterized by the lack of synchronization and reactive power problem. So this is a very interesting topology of common DC bus architecture integrated with renewables. So we have a isolated step-down transformer, then we have a central converter, voltage source converter which can have a bidirectional power, and then we have a fast charging port, then regular charging ports with a common DC bus, and on the same there is a optional stages that we can put the power with the wind as well as with the photovoltaic, and we have a power from fuel cell as well as the battery. So this battery provides the you can call it intermittency of the renewable power generation, and well, so you can charge because fast charger are there, so you can take power from the grid, you can take power from battery, you can take power from the wind, solar as well as from fuel cell, and then if you have a surplus power and battery it's on, then you can put a constant power feedback to the this medium power voltage grid. So this comes a very interesting microgrid topology for DC bus charging station concept. So well, coming to components of off-board EV charging system, typically is input filter, central converter, line frequency or high frequency isolation transformer, AC to DC converter, DC DC converter, and output filter. Now coming to central converter, the central converter stage has a fundamental role in the DC charging architecture and is desirable to provide several features such as distortion-free input current, fully adjustable power factor, and reduced size of the input filter, and reduced number in both active and passive component. Now this is typically, you can see how it is a phase shifting transformer to provide a concept of like a equivalent to 12 pulse. So off-board charger with central grid connected two-level voltage source converter. So what it is interesting here that we have a typically the phase shifting of 30 degree between the two converters, and these two converters are feeding the DC to separate buses. So here you are able to reduce the harmonics on the grid side by both the way, increasing the equivalent to 12 pulse, as well as typically by low frequency pendulum you can easily have a central current on the grid, and you can have a bidirectional power flow for central inverter. Now coming to this another central inverter, that is typically off-board central grid connected VNR rectifier, and this is for of course unidirectional power flow. So here again you are able to get perfect correction for this central converter charging, and you get the typically midpoint also for the typically if you want to require the voltage of different level. Then another is your 3-phase AC buck boost converter, and you can just see clearly after your diode bridge we have a buck boost converter with the capacitor LC capacitor feedback for the central inverter. So this is another topology for central inverter. Then this is another topology with the switch rectifier with LC filter, and this rectifier is a kind of provide the buck converter operation, and with LC you can call it with the inductive filter LC filter, that it provides the typically a good kind of battery charging current like, and with the input LC filter. And this is another topology with the, you can call it a for central inverter. Here we have multi-pulse concept of equivalent to 12 pulse with ripple injection, and with DC you can call it active filter, which really give the power factor correction as well as it give a harmonics reduction even on not only AC side but DC side also, like, and you can certainly go for a little higher voltage. Then you have another central inverter, three-phase edge bridge, 3 edge bridge on 3 phases, which certainly with the bidirectional features. And the advantage of this that you can have 3 single phase topology on 3 phases, and you can have a power factor correction on the primary side. Like, then this is another 3-level neutral point converter for balancing lag of the DC link voltage, and you can easily have a bidirectional features also in power flow here also. And of course, you can reduce the switching frequency as number of levels are increased here for 3 level. There is another high power DC-DC converter. You can call it like a kind of multi-channel or multi-channel interleave buck converter for the second stage of high power DC-DC converter to increase the rating, as well as it provides the less ripple on your DC link capacitor. And of course, you can have a bidirectional feature from each. So all 3 converter can feed the power simultaneously for low voltage battery. This is again a high power DC-DC converter with the bridge, and then isolation of the transformers and rectification for the battery pack with the phase shifted 0 voltage switching full bridge converter. And this high power DC-DC converter, this is again have LLC resonant converter. You can see capacitor connected in series which block the DC going to the transformer winding, and it really provide typically the isolation as well as rectification. There is another topology with the high power DC-DC converter with the, you can call it interleave concept, 2-channel interleave 3-level DC-DC converter for EV fast charging. As you can see here, the 2 edge bridge is connected there with the typically for 2 lag. And this is your high power DC-DC converter. Again, 3 interleave buck converter. All 3 are connected parallel. The advantage that the source current also remain continuous, because at least some are conducting, and you get output current also continuously from all 3. You can call it the phases. Then this is another high power full bridge LLC resonant converter. The advantage of this LLC region, this capacitor provide the blocking of DC going to the transformer. Apart from it, also provide the resonance for the soft switching of the devices. Like, now coming to design of unidirectional converters for offboard electric vehicle charging system. So this is example 1 buck type of PFC topology with the switch rectifier. So in this case, you have LC filter, and as well as you have the bidirectional switches for each phase. And for the buck converter, so it's inherently provided the power factor of the supply, as well as you get the control output DC voltage in this buck type power factor correction switch converter for charging up. So this was switch rectifier, an example, an application case of 7.5 kilowatt unity power factor rectifier system, dimensions that provide a constant voltage 400 volt for operation of a mains from 230 volt phase voltage, ACR 230 plus minus 10, and switching frequency of 36 kilohertz. And semiconductor voltage and current discharge, the maximum voltage discharge on the line diode Dn plus Dn is defined by the line voltage, and that is equal to Vdn equal to Un line to line equal to root 2 root 3 UA RMS 1 plus 10%, and that is around 620 volt, and UDF maximum, that is UT maximum, root 3 by 2 UN LN maximum, that is 537. So selection of blocking voltage, capability of the power transistor and diodes have to consider an additional safety margin delta for the undesirable oscillation of the rectifier input voltage in case of low passive damping of the input filter. Therefore, a 12 volt power diodes and IGBT, from delta equal to from in between 48 to 55 or 90 100 volt MOSFET delta equal to 40 are suitable for the full silicon implementation of the switch rectifier. So coming to current discharge of bidirectional switch SY and DY. So with the defined modulation index M, the average RMS currents of the 2 transistor and diodes forming a bidirectional switch finally result in ID by SY average is ID M2 minus 3 by 2 pi, and ID Y upon S equal to IDC under root M square minus root 3 divided by 2 pi. And the characteristic test of rectifier diodes Dn plus and Dn minus. The average and RMS current of rectifier diodes can be calculated. ID average equal to ID M root 3 by 2 by pi, and ID RMS equal to IDC under root M upon root 3 by 2 pi. And the current test of fast diode df plus and df minus id average equal to idc in bracket 1 minus 3 root 3 by 2 pi m and idf rms idc under root 1 minus 3 root 3 upon 2 pi into m. So coming to current stress on power transistors TS plus and TS minus, the average and RMS currents of PWM modulated transistor are determined IT average equal to IDC M 3 root 3 by 2 pi and IT RMS equal to IDC under root 3 root 3 M upon 2 pi. Now coming to a passive component, voltage and current stresses. The voltage across each DC inductor L is equivalent to half of the value of maximum allowed line to line input voltage UL, and then that is UL plus UL minus equal to UL LN equal to UL plus UL line to line maximum by 2 equal to 310 volt, and the current flowing through inductor is defined by the full load DC current IDC and current triple delta I LPP max, which is limited to given value, that is 25% of IDC. The current triple peak to peak value and the RMS value of the DC inductor delta ILPP and ILRMS can be determined as follows. And this is IDC equal to PO upon UPM and delta ILPP max equal to root 2 by 3 UPN by L in bracket 1 minus M upon FP and ILRMS equal to under root IDC square plus delta IL square PP max divided by 18, and the inductance value of DC inductor can be then selected according to L much greater than root 3 UPN divided by 2 delta IL PP max 1 minus M divided by FP. So selecting the output capacitor, the value of the control output voltage UPN at the additional overshoot margin to enable safety operation during low tangent around 10% of UPN must be taken into consideration. So you see much greater than 1.1 UPN, that is 440 volt, and the RMS value of the output capacitor current delta IC RMS and the peak to peak value of the output voltage level delta U are given by delta IC RMS under root delta IL square PP max divided by 18 and UC PP equal to UPN upon L in bracket 1 minus M divided with 8 FP square C, and the capacitance value of the DC output capacitor can be determined according to C much greater than UPN divided by L in bracket 1 minus N divided by F 8 FP square into delta UC PP max. So coming to example 2, VNR rectifier application for EV charging. So you can see circuit of VNR rectifier with the bidirectional switches. Then the key system specification parameter input voltage, the AC 208 line to line at 60 Hz and AC 400 line to line 50 Hz and input current 4 ampere RMS and output voltage 600 DC at nominal 208 and 700 volt DC bus at nominal 400 and output current absolute RMS value 5 ampere, pulse maximum 10 ampere, and power rating 1.2 kilowatt at 3 phase 208, 2.4 kilowatt at 400 volt, current EAD less than 1% rated load with 208 and less than 4% rated load with 400 volt, and efficiency peak 98%, average efficiency 97%, and primary filter inductor 3 millihenry and output capacitance 180 microfarad and pendulum switching frequency 150 kilo. And these are typically for the inductor design, how the current varying during the under voltage at the input of the filter. So inductor design, the input inductor filters out the switching frequency harmonics, and inductor design amongst the other depends on the calculation of current ripple and choosing a material for the core that can tolerate the calculated current ripple, and the voltage across the inductor is given by V equal to Li di upon dt. And for the VNR rectifier, this equation can be written as V plus by 2 minus V equal to Li in bracket delta IP P divided by d dash TS, where TS equal to 1 upon F W S sub is the switching frequency, switching period, and d dash is the duty cycle for which the switches are on. And for control design, D is assumed to be the voltage at the other terminal of the inductor and is related to D dash, and D dash equal to 1 minus T, and reasoning the current ripple at any instant in the AC waveform is given as delta IPP equal to D dash TS in bracket V bus by 2 minus V in divided by Li. And now assuming modulation index to be MA, the duty cycle can be given as D dash equal to MA into sin omega t, and assuming that Vn equal to D dash into V bus by 2 and delta IPP equal to V bus by 2 into TS into MA into sin omega t into 1 minus MA sin omega t divided by Li. So to get the maximum ripple value differentiating with the delta IPP equation with the respect to time, delta IPV dt equal to k in bracket cos omega t 1 into 1 minus ma sin omega t minus ma sin omega t into cos omega t equal to 0, which gives the maximum ripple exists at sin omega t equal to 1 by 2 ma. Substituting this value, the inductor design delta p maximum v bus by 2 into ts upon 4 li, and li equal to v bus by 2 divided by 4 sf sw into delta ipp max. Now coming to bus capacitor selection, the bus capacitor is responsible for removing the ripple on the DC bus on the DC voltage that can be caused by the draw of sinusoidal current, and the capacitor value at the DC bus are related C equal to 1 by 3 into P by 4 into F in bracket V square minus V minus delta V square, and above equation is used to select the minimum D bus capacitance value. And example 3, LLC resonant full bridge DC-DC converter, as you can see in the circuit. So here resonant inductor and capacitors are connected on the primary side of the transformer in this full bridge converter, full bridge rectifier. And here of course we can call it equivalent resonant circuit, where we apply the kind of a square wave and with the resonant circuit and the transformer equivalent. So now coming to converter voltage gain, converter gain, that is switching bridge gain multiplied resonant gain multiplied the gain transformer ratio NP upon NS. So K as a function QM Fx equal to VO AC and Vn AC and equal to Fx square into 1 m minus 1 and under root m Fx square minus 1 square plus Fx square into F square Fx square minus 1 2 square and dot m minus 1 square into Q square. So now where Q is under root L upon R upon AC, that is quality factor, RAC is 8 upon pi square and P square upon NS square into RG, reflected load resistance, and Fx equal to F, small fs upon Fr, normalized switching frequency. So now coming to Fr equal to 1 upon 2 pi under root LR CR resonant frequency, and M equal to LR upon LR plus LM upon LR, ratio of total primary inductance to resonant inductance. Now coming to modes of operation, at resonant frequency operation, Fs equal to Fr, and above resonant frequency operation, Fs is greater than Fr, and below resonant operation, Fs less than Fr. And this is typically how you can see modes of operation. I mean, in this case here, well, resonance is below, resonance is above, and then the power delivery operation with resonant tank excited with positive voltage, and typically with the power delivery when the resonant tank excited with negative voltage, and this is freewheeling operation during the positive half cycle. This is your freewheeling operation during negative half cycle. And at resonant frequency Fs equal to Fr, you can just see how the gating signals are given and how typically your typically inductor current and magnetizing current and diode current and your typically diode currents are there in the, and as well as the switch voltage typically. So if above resonant frequency operation, I mean Fs is greater than this, so you can clearly see the waveform how the soft switching is opening, and then the Fs less than this Fr, so how this switching is taking place. Now coming to DC fast charging, which is very prevalent on highway. I mean, you can just see clearly, I mean, how they look like. And here for DC fast charging, we have a low voltage AC grid which rectified into DC, and then we have a BESS 1, BESS 2 with the DC EV side, DC fast charging station typically in the grid. So we have a typically even several battery energy storage also, which really give additional energy in addition to, and otherwise when the fast charging is not there, they get charged to provide the fast charging also. So for this fast charging, you can see the grid transformer, then input filter, line reactor, and then we have typically the VDC by this line rectifier, and it's fed to DC-DC converters, different DC converter with the charging ports control unit. And this is the topology for DC fast charging station with your let's say your distribution transformer followed by harmonic filters, then AC to DC converter, and then we have a DC-DC converter, even with the energy storage as well as renewable also, maybe from the wind and solar, and then of course we have a DC converter for EV charging. So you can have for fast charging you can take from energy storage, you can take even renewable also as well as from the grid. So all three sources can give the fast charging without exhausting the grid to very high pulsive power. And this is typically for DC-DC fast charging system. So you have a kind of a 12 pulse converter with unilateral back-to-back converter and several. The common DC bus is powered for several vehicle charging like. This is again another topology. Here you have other load also, and here you have your multi-level inverters and isolated DC-DC converter, which is responsible for several battery charging system of cascaded level multi-level converter. And these are basically topology for DC other. So you have AC-DC converter, then your battery storage and DC-DC converter. So charging stand with cascaded multi-level converter with the split strategy. And then this is the typical topology for high frequency transformation. So you have a battery storage. How from battery storage we are providing the power. So you have a grid, and from grid we have a typically multi-level matrix converter, and from matrix converter we give for high frequency transformer which charges the battery, and you can take the power from the battery, and then you really have a 3-leg inverter for the fast charging, power flowing into the battery. So the topology for DC fast charging station, we have a like a mini, maybe bidirectional or unidirectional, and with the grid support, then renewable integration, or we have a best integration and power to increase the power density and reliability component, control complexity. So these all 5-6, typically the 6 topology are compared here. Now converter for DC-DC fast charging. So you have typically LLC filter after diode rectifier, and then you have a typically the DC side switch and diode for controlling the kind of boost converter, unilateral boost converter for the bulb. And then you have a typically another VNR rectifier for the purpose. Then you have a 3-phase 6-factor with LC filter. Then you have a central connected multipulse rectifier with DC active filter. Then you have a DC bus, dual DC bus 3-level motor balancing lag. Then EV charging is a 3-phase VNR rectifier plus full bridge LSD converter after the VNR rectifier. So you have a typical to increase the rating, you can put several DC resonant converter. And then the charging station resonant full bridge LC topology may be connected in parallel to enhance the rating. So coming to now, this was off-board charger. Now coming to on-board charger, which are normally on the vehicle. So classification of this charger, on-board charger, is like maybe single phase, 3-phase. So in 3-phase, single phase also may be isolated, non-isolated, unidirectional, bidirectional, with a conductive, inductive, like a wireless, and maybe typically independent or integrated. Integrated, which is taking the typically the part of the vehicle, the inverter and vehicle winding. The 3-phase may be isolated, non-isolated, again unidirectional, bidirectional, conductive and inductive, wireless, and integrated or band. So coming to on-board charger, which normally of low rating. So we have a normally AC-DC converter, then followed by power factor correction converter, maybe boost converter with the DC, and then DC-DC converter for controlling the battery charging current. So the control diagram for an isolated, for an on-board charger of normally of lower rating. Because weight is the issue on putting the vehicle. Coming to universal, your on-board charger topology. So we have a diode rectifier followed by the boost converter, and then we have a unidirectional DC buck converter for the onboard charging system. Then we have integrated unidirectional. So we have a internally unidirectional by chargers, and then we have a unidirectional DC-DC converter. So for increasing the rating, we put sometime this integrated unidirectional charger also. And then this is typically single phase unidirectional multi-level charger, and where here using, so it serves the increases the number of level as well as it provides the power factor correction also, and give the control output DC voltage also for next stage of your unidirectional DC converter. These are typically unidirectional isolated onboard charger topology. So general block diagram for you. So it consists of AC grid with the rectifier, then we have a DC and with the power factor correction, followed by the DC isolated DC-DC converter with the isolation with the of course rectification and to charge the battery. So this is most simplified topology of this, that we have a single phase PFC, we call bridgeless PFC on the input side. Then we have a isolated DC-DC converter with the bridge, and then we have a rectification for the battery. There is another topology, unidirectional isolated onboard charger using series unit converter with boost PFC. So we have after direct boost for perfect correction converter, followed by the your series resonant isolated DC converter. This is the most simplest conventional single phase bidirectional topology, voltage source converter with bias. So we have a typically here a voltage source converter for perfect correction, bidirectional power flow, and then we have a typically you can call it a bidirectional buck boost converter for charging the battery. It can feed the power back as well as it can charge the battery also. So this is typically a bidirectional for three phase. So a conventional three phase bidirectional topology like three phase voltage source converter followed by your DC-DC converter for stepping down the voltage. So this is also by bidirectional power flow, normally preferred for little higher power rating. And this is your bidirectional isolated DC converter. So we have HB for perfect correction and regulating the DC link voltage. Then we have isolated DC-DC converter with the dual active bridge, and then finally with the filter we have a for battery charging. So this is your bidirectional AC-DC matrix converter topology for the battery charging, which give a perfect correction and control charging current in the battery. And this is your bidirectional conventional bidirectional. So we have a three phase voltage source converter followed by half bridge DC, you can call it half bridge resonant converter, and then we have a voltage source converter on secondary side with the switch capacitor followed by capacitor inductive filter. So it can have a bidirectional power flow and it provides the resonating circuit for soft switching. There is another converter with the bidirectional power flow, matrix converter based bidirectional isolated topology with high frequency transformer isolation. So we have mic filter followed by matrix converter, which give the this into directly low frequency into high frequency, and then we have a transformer followed by the rectification for charging the battery. So this is integrated topology. The integrated topology normally what we have a power integrated system. In this case, we can have a single phase or three phase input, and then we use the three phase winding of the motor, drive as well as inverter of the typically of motor drive for feeding this high voltage and low voltage battery both. So you not to put a separate charger, only you have option for switching from typically from the grid for single phase or three phase. And these are typically indicated side converter positive buck boost diode rectifier. So you have a direct rectifier with buck converter, and then you have a topology for charging the battery. So this is you connect the typically the grid here, and considering that the vehicle is at its standstill, it's not used, its motor is not even. And there is another topology for indicated converter buck boost bridgeless topology for direct AC-DC converter, bidirectional converter, integrated DC-DC converter. This is another topology or off-board as well as on-board, which is using the squirrel cage induction motor winding as a filter, and then the inverter for charging the battery. So it really takes the power from the grid for the purpose of charging, and when your vehicle is moving, of course, the supply is disconnected. So it's an interesting topology that you just putting a MI filter with the rectifier and then connecting to input of this converter, like which we have as a three, you can call it the buck boost converter. Like there is another topology of integrated topology with the if it's electronic motor drive both rectifier and DC-DC converter, because this kind of converter, except the input converter, you are using the same windings as well as the devices of the converter with single phase AC supply for battery. There is another topology of integrated using three phase PMSM, which is used for, so you have a three phase grid connected to this system, and then this inverter is working as a rectifier for charging the battery, and this winding is used as a filter at the input line. And there is another topology for electronic motor based integrated charging. The winding is used typically as an inductor of the input. And this is the wireless topology. Wireless topology also coming from very important case of with active front. So we have active front converter, high frequency inverter. Then we have a high frequency transformer, which really give the isolation. We have a primary coil, secondary coil, and rectification battery. So the wireless charging is very popular because of many reasons. And these are typically wireless topology. So we have you can call it the bridge converter, followed by a primary side LCC network, and then secondary side network, and both sides you will find the series capacitor, and this series capacitor blocks the DC component going to the transformer. Apart from that, it gives the reactive power requirement also, or magnetizing current requirement of this isolation transformer, which have a large gap in between the two primary and secondary winding. There another topology of wireless, the high power density jet source wireless charger with line frequency transformer charging, and this is another topology of wireless high power density jet current wireless charger with line frequency sinusoidal charging. So now coming to component of onboard EV charging system, we need the EMI filter, line frequency rectifier, HDC converter, and power factor correction converter, isolation transformer of medium and high frequency, and DC-DC converter. So coming to power factor correction converter for low voltage and low light electric vehicle charging system. So here we have a problem with the state of art converter configuration. So we have a boost PFC plus series unit converter with the isolation and the feature with the high power factor, then boost PFC LLC isolated, and then high, and then boost PFC with PSFB. So the development of this single phase is taking care of the power factor correction stage as well as battery profile. So here you can we have a power factor with the control, we have power factor correction which regulate the voltage and have a sinusoidal current on the input, and then we have a DC-DC converter which is really responsible with the filter to charge the battery in dual stage architecture, and we have a single stage architecture where this active PFC converter itself responsible for charging the battery. Of course, the converter depends what you use. Sometimes buck boost converter which responsible can control the voltage and charging as well as power factor correction also input supply. Now coming to giant modeling and implementation of non-isolated single stage power factor correction converter for light electric vehicle charging. So these are typically a non-isolated quadratic buck boost AC-DC converter for light electric vehicle charging. So this is where you can see how this converter and responsible for charging. So it has a salient feature, single stage component, compact structure, quadratic buck boost gain, enabling higher step down gain capability, and the discontinuous current operation of inductor facilitate the inherent power factor and simplified control and reduce sensor requirement. And these are the three different modes of this quadratic buck boost converter. When typically device conducting, diode conducting, and none of the two conducting for battery charging. And these are the waveform of this quadratic buck boost PFC converter, and these are the typically the voltage gain equal to V battery 1 V in D1 square upon D2 square, and relation between V and I to take care of inherent power factor and the capacitor voltage, and then the critical conduction parameters like for design. And these are the typically the design equation for the value of inductor and selected calculated value and selected value of capacitors, inductor, output capacitor, then filter capacitor and inductor. There is another 12 non-isolated stage capacitor and coupled inductor based modified zeta converter for light electric vehicle. And you can clearly see how it is really the perfect. So its salient feature is single stage, single switch, compact structure, high buck boost, step down gain, reduced magnetic volume through inductive coupling, and DCM operation of inductor facilitate inherent PFC and simplified control and reduced sensor requirement. And these are the different modes: the device conducting, diode conducting, and now the two conducting, battery charging. And these are the typical waveform for these all parameters, voltage and current. And these are the gains like M equal to D1 upon D2 in bracket 2 minus D1. For the condition for DCM, the D1 should be less than this value of capacitor voltage, and this is now coming to selection of coupling coefficient. The following conditions are considered with designing coupled inductor, particular K, which is a coupling coefficient of the inductor, and is listed high frequency input current and output current. So during mode 1, delta IF is given here V in minus VC LF, K VC1 K V battery minus VC divided by root LF L2 K1 minus K square plus K square V in minus VC divided by LF into 1 minus K square into D1 TS. Similarly, delta IL2 you can get it K VC minus VC V in divided by root LF L2 1 minus K square plus VC minus VC1 minus V battery divided by L2 into 1 minus K square into D1 TS. So similarly, during mode 2 we can have a represent delta IF at T1 TS in bracket V in LF minus 2 VC upon LF plus K V battery under root LF L2 1 minus K square plus K square V in minus 2 VC upon LF into 1 minus K square by close D2 TS. Similarly, delta I2 for K2 VC minus Pin divided by under root L21 minus K square minus V battery divided by L21 minus K square D2 PS. And during mode 3 also we can have a delta IA equal to in bracket V in minus VC divided by LF into 1 minus D1 minus D2 into TS, and VC1 equal to minus V in K under root L21 LF multiplied D1 plus D2 minus V battery D1 plus D2 divided D1 plus D2 plus K under root L2 upon LF into D1 plus 2 D1 2 into D1 2 upon D1. And this is typically the input current variation with different values of the K. You can see how it is performed. And this is the value output current ripple with the different value of K. This is a couple inductor with minimum coupling effect with the air gap. Now you have in between gap, so that really avoids the saturation and to keep the inductor constant. And these are the, of course, the design equations of different inductors, capacitors, element, and then the calculated value and the selected values of the. And this is the control implementation of power factor correction. Both converter control using a single control loop, and control loop takes care of battery charging, while for constant current charging, and where you are setting the I reference for DSP implementation. And these are the typically design parameters. For this varying voltage 162, 50, 220 nominal and 450 watt power, the 48 volt, and battery voltage were range 36 to 20 kilowatt. And these are the typically simulated results. You can see supply voltage and supply current in phase with the battery voltage and battery current, and then the voltage of switches and diodes. And typically the change performs with the change of inductance, but power factor, the wave shape as well as the the power factor remains constant with respect to the variation in the your typically the voltage increase or decrease. And this is a change of, typically you can call it the charging current. As you increase the charging current, certainly you decrease the charging according to supply current adjusted, but remain in phase with the supply voltage and sinusoid. These are typically hardware result, but it is used the hardware result for developing this, typically the charger. And these are the, of course, the different optocoupler circuit, then your TSP as well as the current and voltage sensor signal circuit. And these are the experimental result, voltage and current waveform, then battery voltage, battery current, and typically the switch voltage, switch current, and inductor current, proving that it's in DC, so that you get inherent power factor. Then supply voltage increase and decrease the performance, and charging current increase and decrease. And then the simulated and experimental performance, so you can see clearly even 468 watt also, at even 163, TID 3%, power factor unity, and even 217 volt also, power factor unity and TID 2.1%, and at 253 volt with the 465 watt, it says TID power factor unity and TID of supply current only 1.7%. And this is typically the, you can go simulated for this SSC converter, and you can see with the performance with increase and decrease in voltage. And this is the experimental performance corresponding to that, how really converter operating typically input voltage, input current, and then typically your battery voltage and battery current. This with the increased performance with the hardware result of increased voltage and decreased voltage, and the your load variation means the charging current increase and decrease of the battery. And this is typically the power quality performance. Even at typically at 158 volt, it give a 2.5% TID power factor unity, and 220 also it give a power factor unity and 2%, and at 253 volt also it give a 2.7% TID and power factor unity. Now coming to design, modeling and implementation of bridgeless non-isolated single stage power factor current converter for low voltage electrical charging. So they typically a non-isolated coupled switch inductor SEPIC HDC converter for light vehicle charging. So you can see the bridgeless charge, typically bridgeless version of the SEPIC converter for battery charging and with the high gain. The single stage, single switch compact structure switch, and eliminate the conduction losses associated with slow diodes, extended buck boost gain, enabling higher step down gate capability, and this current mode of inductor facilitate the inherent power frequency and reduce sensor requirement. And these are the typically like when switch is conducting, when the device diode is conducting, and none of the two are conducting. And these are the waveforms of voltage and current of different parts of the inductor, capacitor, switches, and these are the, of course, the gains, voltage gain and other parameters. And these are the design equations as well as design calculated value and selected value for the inductors as well as capacitors like. There is another non-SL semi-quadratic gain AC/DC converter for light electric vehicle charging. With the single stage itself, it is able to give quite high gain, and it comes as a bridgeless configuration. So eliminate the conduction losses. So it's slow diode which activate extended buck boost gain, enabling higher step down gain capability. ECM operation of inductor facility enhanced PFC, perfect correction, simplified control, reduced sensory comment. And these are the when switch is conducting, when diode is conducting, and none of the two are conducting, and the corresponding waveform of different components, and the gain, voltage gain, and other critical parameters, and then the design equations and design calculated value and selected value of component. And this is typically the control, digital control impedance in the DSP, and these are the parameters of this 450 watt charger, and these are the simulated result: supply voltage, supply current, battery voltage, battery current, and you can see the even the typically inductor currents showing the discontinuous, so that you get inherent power factor action without changing input voltage, input current. And this is the effect of voltage change as well as the charging current change. And these are experimental results which circuit is developed with the, you can see inherent power factor correction, current is in phase with the voltage, and you have a battery current and battery voltage, and again all component voltage and switch voltage, switch current. Then the change on voltage, increase and decrease of supply voltage, and change in the loading, your charging current, increase and decrease, and the power quality performance. So you can see at 160 volt, even at 415 watt, you get the 2.5% TAD, and at 220 you get the 2.47%. With all cases power factor is almost unity, and typically at 247 volt also it gives a power factor unity and 3.1% TAD. And these are the typically the simulated waveform of this SQ converter. And you can see supply current and supply voltage are both are in phase, and battery voltage, battery current, and then other component voltage and current. This case of simulated converter with supply voltage, fluctuation, load, and the load, you can see charging current variation. These are experimental result of this converter. You can see supply current are in phase, and battery voltage and battery current, and the different components voltage demonstrating the inherent power factor correction, and then the result for voltage variation as well as the charging current variation, and the power quality performance. You can see the TAD 3.9%, 4.3% at nominal voltage, and at 258 4.7, but power factor is unity in all cases. So now coming to design, modeling, and implementation of isolated single stage power factor correction for power factor correction converters for light electric vehicle charging. So is the case with the simplest one converter for flyback, isolated boost flyback based converter for light electric vehicle. So you can just see how the typically the boost flyback is operating with the isolation. So it has simply single stage isolated single switch compact system, extended buck boost gain, enabling higher step down capability, and isolation between the grid and the battery side, and reduced magnetic volume, and DCM operation of magnetic inductor facility, the inherent power factor correction, and simplified control, reduced sensory command. And these are the modes: band device conducting, band diode conducting, and none of the two are conducting. And these are the typical waveform of all three modes. These are of course the voltage gain, and these are the design equations, the design calculated value and selected value. This is the control of this converter, and these are the specifications for the charger which is developed. And these are the typical simulated result. You can say supply voltage, supply current, battery voltage, battery current, and typically the you can call it the your LM current, L1, L1 current. And these are of course you can say simulated result for battery voltage fluctuations and battery current charging increase and decrease, and experimental result for inherent power factor correction with supply voltage, supply current, and battery voltage, battery current, and the device component, and then the increase and decrease in the voltage, and as well as the battery charging current and decrease and increase of battery charging, and the power quality performance at 169 volt also you get the power factor unity with 2.9% TAD. At 214 volt it have a 4.4% TAD power factor unit, and 254 it give again power factor 0.9 with a TAD of 6.8%. Now coming to design, modeling, and implementation of bridgeless isolated single stage power factor correction converter for light electric vehicle charging. So this is, you can clearly see the isolated modified SEPIC based ACD power factor correction for LV charging. So you can clearly see with the how it is a bridgeless version of this SEPIC converter with the isolation is working here for battery charging. So it has a advantage single stage isolated compact then extended buck boost gain, enabling higher step down capability, isolation between grid and battery side, reduction in losses power due to the low frequency diode, and DCM operation of magnetizing inductor facilitates the inherent PFC and simplified control, reduce sensor requirement. And these are the modes: when switch is conducting, when diode is conducting, and none of the two are conducting. Then the corresponding waveform and the gains, what is gain and other parameters, and then the design equations for different components, and the design calculated value and selected values of component for development, then the control of it, then the specification of it, and then the simulated result is supply voltage, supply current, and battery voltage, battery current, and the other component inductor voltage, the capacitor voltage, and inductor current for inherent power factor correction. And then the increase in voltage, input voltage, and decrease in input voltage, still power factor is maintained, and then the increase in charging current, decrease in charging current, and the experimental result for the same, the supply voltage, supply current, which remains in phase, the battery voltage, battery current, and the different component voltage and current, like demonstrating that even the inherent PFC also, and the increase and decrease the voltage, and increase and decrease in charging current, and the power quality performance. At 163 volt, it has TAD of supply current 1.7% with unity power factor, and at 220 volt also it has a power factor unity, and total autonomic distortion of supply current is 3.1%, and at 250 volt also it has a unity power factor and 2.3% TAD of supply current, at typically at 470 watt rating. Coming to the numericals, so coming to example 1, a simple buck boost converter is used for battery charging 50 kW switching frequency with a DC input PI equal to 700 volt. The output voltage, battery voltage is V equal to 350 volt. The battery is charged with a constant current of 20 ampere. Determine the value of output filter inductor L such that the peak to peak inductor current will delta I 10% of the DC component I0. Determine the peak to peak steady state current I max. Design an inductor which has the value of L and I max from parts A and B. Use the Faraday core with the B max 0.8 Tesla. Choose a value of the winding resistance 2 ohm, room temperature, calculate the core size, gap inductance, wire size, and number of turns. Assume resistivity of copper 1.7 to 10 power minus 6 ohm, and probability of air mu0.45 into 10 bar Henry per meter. The coming to buck converter duty is D equal to V upon VI, so it comes like 0.5, and buck converter peak to peak ripple delta I equal to VI minus V into D upon L into F switch, so delta I taken 10% of DC current, that's I equal to delta I 0.1 into 22 amperes. Now inductor is VI minus V into D upon delta I, it comes 1.75 millihenry, and peak to peak, the peak steady state inductor current I max equal to delta I0 equal to delta I2, it becomes 21, and core geometrical constant Kg must be greater than rho L square I max divided by B max square RKU into 10 power minus 10 in centimeter to power 5. So this comes, Kg comes like 0.3638 centimeter power 5. To form E core preferable, the core E50 selected, which is enough to certify the quality, and core E has a Kg equal to 0.909 centimeter or 5. Dimensions are AC equal to 2.26 centimeter square, WA equal to 1.78 centimeter, MLT 10 centimeter, and LM into 9.5 centimeter. So air gap is LG equal to mu0 Li square 10 power 4 divided B max into AC, and it comes with the calculation 6.71 millimeter, and the number of turns N equal to L I max divided by B max AC into 10 power 4, it comes 203 turns, and wire size AW has to be less than KW, W upon N into centimeter cube, so it comes 4.38 minus 3 centimeter square. Now coming to design example 2, design the flyback transformer for the converter listed in figure. This converter operates with the input voltage of 325 volt and produces an full load output of 24 volt at 10 ampere. The switching frequency is 70 kilowatt. Under these operating conditions, it is desired that the converter operates in the continuous conduction mode with the magnetizing current equal to 20% of DC component and of magnetizing current, and the duty cycle is chosen D equal to 0.33, and the turns ratio M2 upon N1 is 0.15, and copper loss of 4 watt is allowed, and not including proximity effect losses to allow the room for the isolation between the primary and secondary windings. A fill factor of K.3 as ohm, a maximum flux density P max 0.25 Tesla joule. This value is less than the worst situation. B saturation of Faraday core, and assume the resistivity of copper 1.724 into 10 power 6 ohm centimeter, and probability of air mu0 equal to 4 pi into 10 power minus 7 Henry per meter. So these are typical circuit of flyback converter schematic and waveforms. And coming to now for solution using capacitor charge balance, that is component of magnetizing current can be found by Im equal to N2 upon N1 into 1 upon D dash into V upon R 2.25 ampere. And the magnetizing current levels will be delta Im equal to 20% Im, that is 0.45 ampere, and the maximum value of magnetizing current is Im max equal to Im plus delta Im, that is equal to 0.7 ampere, and magnetizing index Lm equal to Vg TTS upon 2 delta Im equal to 1.72 millihenry. Now RMS value of primary winding current I1 equal to Im under root D in bracket 1 plus 1 by 3 delta Im upon Im square equal to 1.31 ampere, and RMS value of secondary winding current I2 equal to N1 upon 2 into Im under root D dash under root 1 plus 1 by 3 delta Im upon Im square equal to 12.33 ampere, and total RMS winding current is I total equal to I1 plus N2 upon N1 into I2, that is 3.16 ampere. And kg now necessary core size kg much greater than rho Lm I total Im square in 10 power 6 P max PCU, putting value it comes 0.495 centimeter power 5 from E core. For core E50 is selected, which is large enough to satisfy the above inequality, and core size kg 0.99 centimeter, 5 dimensions are AC equal to 2.26 centimeter, W equal to 1.78, MLT 10, and M 9.58, and LG is the formula usual Lm Im square M Bmx square AC into 10 power 4, it comes 1.12 millimeter. And the number of terms N1 Lm Imax upon Bmax AC, so it comes like 82.19, that's 82 turns. Since integral value has to select N2 equal to 0.15 and 1, it comes 12.3 third term. So integral value selected, the fraction of winding current allowed to winding 1 and 2, so alpha 1 equal to I1 upon I2, and it comes 0.414, L2 equal to N2 I2 upon N1 I total, so it comes 0.585. And the wire gauge should be selected AW1 equal to less than L1 KU W upon N1, so it comes 2.69 10 to power minus 3 centimeter square, and AW2 L2 KU WA upon N2, that is 26.03 10 to power minus 3 centimeter square. Now coming to typical question 3 or example 3, a single phase uncontrolled bridge converter supplied to 30 volt 50, consider constant load current of 15 ampere, compute the average output voltage, resistance factor, displacement factor, power factor, AC mains current, diode current, R1 current, and the input power and the reactive power. So you have a diode rectifier with inductor filled with the load, the given supply voltage and frequency 50 Hz, DC link current I0 equal to 15 ampere. In single phase uncontrolled bridge converter, the waveform of supply current is square wave with the amplitude of DC current I0. So moreover, the RMS of fundamental component of square wave 2 root 2 divided pi into 0.9. The amplitude of it, therefore the supply RMS current I0 is equal to I0 equal to 15, and fundamental RMS IS1 equal to 0.9 I0 13.5 ampere. Average output voltage VO equal to 2 Vm by pi, that is 207.0728 volt. Distortion factor is fundamental current divided by supply, so IS1 upon IS, that comes 0.9. Displacement factor cos phi theta 1, it is 1 since the diode in phase with the supply voltage, and power factor dVf into dF, so it comes 0.9. And the AC mains current IS equal to I0 15 ampere, diode average current ID average 0.5 I0, that is 7.5, diode RMS current your root 2 I0, that is 0.707 I0, 10.61 ampere. Equivalent load resistance R equal to VIO, that is 13.805, and diode peak current ID peak equal to Vm upon R, that is 23.56, and input active power PI PSIS PF, that comes 3106.035 watt, and reactive power QVS under PF square, so it comes 151. And peak voltage diode active PI 3 to 5.26. Now coming to typical example of three-phase uncontrolled bridge rectifier used to charge the battery at about 20 kilowatt 400 volt from AC 3-phase 50 Hz. A large inductor is included in series with the battery, a resistance inserted. The charging current load the resistance, DC current RMS and this. So given here with the circuit that the supply RMS is 415 by root 3 root 39.6, and Vm is 239.6 into root, so that is 338.84. We can say supply 50 Hz, power to 20 kilowatt, mean output voltage is VO equal to 3 root 3 Vm upon pi, that is 560.44 volt. So charging current I equal to battery power divided by battery voltage, so that is your 50 typically 20 into 10 power 4, that is 50 ampere, and I equal to 50, Q minus E equal to R that is your 560.44 minus 400 by R. So R series resistance to be included is R equal to 3.208 and DC link current 5T, RMS current is root 2 3 by 2, that is 40.82, and if IS1 is fundamental component, one must be known root 3 VLSI, that is IS1 root 6 I upon pi. So distortion factor BSI 1 upon SI cos pi, so that is IS1 IS cos pi, that is 3 by pi, so 0.9549, and displacement factor cos pi, where pi is angle between fundamental current, so that's here the 0 as pi is equal to 0, power factor is dpf and df, that is 0.9549, and RMS current, diode current is ID equal to IU on root 3, that is 50 upon root 3, that is 28.86 ampere. Now coming to example 5, find the optimum value of DC side inductor capacitor for single switch boost PFC converter. The following specification given in circuit given in figure, and rated power is 1000 watt, output voltage 400 volt, output ripple current less than 0.2 per unit, output current ripple 0.5 per unit, line frequency 50 Hz, supply voltage 230 volt, and switching frequency 40 kHz. So you can see the circuit here. So coming to solution, P equal to 1000 volt, V equal to 400 volt, P output ripple 0.0 per unit, IU ripple is 0.05. So P equal to V0 IU0, so I0 is 0.5 ampere. The operation of the optimum capacitance value V output ripple is IU 0.2 omega C. So C comes I 0.2. So C comes from putting value 497.3 microfarad, and I output ripple is P upon 4 FSL, and L equal to V upon 4 FS into I1. So L comes here putting value 20 millihenry. Now coming to example 6, calculate the output voltage ripple and output current ripple for a single switch power factor with the following specification: rated power 1000 watt, output voltage is 400 volt, DC capacitor of 1500 microfarad, boost inductor 5 millihenry, line frequency 50 Hz, supply voltage 230 volt, and switching frequency 30 kHz. So this is the circuit of boost converter. So here solution, P equal to 1000, voltage 400, voltage ripple 0.02, and current ripple, and V equal to 2.5, output capacitor typically voltage ripple comes 2.65, and the percentage output ripple is 0.066, and output ripple is V upon F. So putting an inductor value, it comes to 26.7%. Now coming to example 7, a single phase unidirectional PFC boost converter draws a 200 watt from 230 volt 15 small variable frequency drive. The switching frequency is 100 kHz. The power factor connected close to unit. It when the value of boost inductor for the current will 5% of maximum inductor current, and the output capacitor sufficient to make that is 400 volt with 1%. So here solution, P equal to 200 volt, P FS is 100 kHz, VD equal to 400 volt, IP equal to V upon V under root 2, 12.297 ampere, I ripple 5% of this, so this 0.6148, and V ripple is 1% of 4 volt. The value of output capacitor is VD output ripple ID upon 2 V omega, so CD comes 2 millifarad, and the value of boost inductor I ripple upon 4 into LD. So from this LD comes 8.1317 millihenry. Now coming to example 8, a 3.3 kilowatt PFC boost converter EV charger is designed for normal input voltage of 230 volt 50 by 60 Hz with the input voltage ranging from 180 to high value 265. Determine the value of boost inductor and peak inductor capacitor if the switching frequency 100 kHz and the peak to equal to 50% of the peak low frequency current and peak nominal voltage. The DC link voltage 330, or ignore the power. So input RMS current is IP equal to P upon V pay, so that comes 14.35 ampere, and peak to input ripple current I page peak is root 3 IPA, so that comes 20.29, and data peak is RI into IPA, so 0.2 into 20.29, that is 4.01, and the duty cycle of typically peak input voltage, so D0 equal to 1 under root 2 cos 0 upon VDC minus equal to 1 minus root 2 PH BDC, so it comes 0.144, and the required inductance L equal to root 3 delta F delta V, so putting value it comes here 115 microhenry, and the peak current in the inductor is sum of the line current. So ILP equal to IP plus delta IL 1 by 2, so it comes 22.32 ampere. Now coming to example 9, a EV charger has input current of 20 ampere. The harmonic components of current are measured as 5 ampere RMS. Calculate the total harmonic resistance. So TAD is your I harmonics upon I fundamental, and I fundamental I total is minus I harmonic. So I fundamental is 20 by, so that comes 19.36. So TAD is your 5 upon 19, so it comes 25.81%. So coming to example 10, a heavy charger have a DC component voltage of 400 volt. If the ripple voltage is measured as 5 volt, it to be calculate the ripple voltage as percentage of output. the well percentage ripple equal to V ripple I ripple. So putting a value 5 upon it comes 1.25, and these are the references from which this material is prepared. And thank you.